Hey everyone, it's Dr. Walker. Let's look at the second example from video 57C on calculating moments of inertia. This time we're finding the moment of inertia of a solid cylinder. It's uniform, that means the density is constant. It has a radius r, mass m, length l. Find the moment of inertia about the central axis. Let's go ahead and get started. First thing we can do is we can write our definition for the moment of inertia. I equals the integral of r squared dm. We know that the next step is to write dm in terms of either a length, area, or volume. In this case, our object is in 3 dimensions, so it has a volume. So we learned in the lecture video that we can write dm as rho dv. In this case, our volume mass density rho is a constant, so it can come out of the integral. So we're going to have rho integral of r squared dv. Now the trick is to figure out, well, how are we doing this integration? In the previous example with the rod, we divided it up into a whole bunch of little mass elements that had a mass dm and they had a length dx. But we don't want to do that when we have a cylindrical shape, because what variable are you going to integrate over? If you have a bunch of these little cubes here, how are you going to integrate in an easy way to get the whole cylinder? Instead, what we want to do, and this is a trick that you just kind of get with practice, when you do another cylinder problem, you'll be able to remember this trick. We're going to do a lot of these in physics too as well, which is why I like to introduce them to you now. What we do is we divide up our cylinder into a whole bunch of cylindrical shells. So it's drawn here in blue. The cylindrical shell right here has a radius r, little r. It has a thickness dr, and it has a length l. So it's easier to just draw one, but if you were to do it like the rod where we drew a bunch of these little elements, right? You would just draw a whole bunch of these shells. And then you figure, what variable are we going to integrate over? With a rod, we just integrated over the length, which was along the x direction. Here, if we have a bunch of cylindrical shells and we want to obtain the whole entire cylinder, then we need to integrate these shells from the 0, or the axes, all the way up to big R. That is how we will get the entire cylinder, integrating the shells along the R direction from 0 to capital R. So with that in mind, our dV here has to be the volume of one of these cylindrical shells. Remember before when we had dx, when we did the rod, that was easy. We just said, oh, well, that's just dx. But now we need to come up with an expression for dV in terms of R, because we're going to be integrating along the R direction. Let's go to the side here and first figure out, let's go back and look at this density. It's going to help us a little bit. We know that density, and this was the density of the entire cylinder. Density is mass per volume. What is the volume of the entire cylinder? Well, it's going to be this area times this length. The area of a circle is pi r squared times the length. So I just wanted to show this on the side because this will make it easier to find our dV for the cylindrical shell. Now that we know the density for entire cylinder, we will plug this value into for density at the end. But now let's think about how to write dV. Instead of needing the volume for the entire cylinder, we just need the volume for one of these little shells. We can use the same approach though. If we can have the area of this shell times the length. That's what we did here, the area times the length. So what is the area of this shell? Well, it's going to be the circumference of the shell, which is 2 pi r, times the thickness, right? If you multiply the circumference times the thickness, you will get the area of this shell. So that's how we're going to write to to rewrite our dV. The dV is going to be the area, which is the circumference. Actually, I'm going to write it down here so I have more room. So our dV is going to be the circumference, 2 pi r, times the thickness, dr. This is the area, just like this was the area. And then we need to multiply it by the length. The length of all of these shells is capital L. Once you have done these cylindrical problems a lot, you'll just be used to substituting 2 pi r dr L for the dV. Just takes a little bit of practice. Let's take out our constants. Our constants are 2 pi and L. So inside the integral, we just have r squared. Oops. I made a small mistake here. Well, it's a big mistake. The area is 2 pi r dr, so little r, right? Because the area of this shell has a radius r. It does not have a radius capital R. So this r has to stay inside the integral. We get r squared r dr. And we're going to integrate from 0 all the way to capital R. So make sure when you look at the area of your cylindrical shell that it has the correct radius. I had put a capital R because I was thinking about the area of the whole entire thing. Let's go ahead and perform our integration. We're going to have the integral of r cubed dr, which is going to be r to the 4th over 4 from 0 to r. And now we can plug in our limits. It's going to be rho 2 pi L times capital R to the 4th over 4. Now we can go ahead and plug in our density. This was our uniform density. M over pi r squared over L was our density. Then we're going to multiply by 2 pi L r to the 4th over 4. And now we just need to simplify. We're going to cancel out the r squared to get a 2 here. We're going to cancel out the l's. We're going to cancel out this 2 to get 2 here. We're going to cancel out the pi's. Lots of things are canceling out. Let's see what we're left with. We're left with m r squared over 2. So 1/2 mr squared. So all this work for a relatively simple expression for the moment of inertia of a uniform cylinder about the central axis. The key takeaway message here is that you're dividing up the cylinder into a whole bunch of cylindrical shells, and the volume of each of these little cylindrical shells is 2 pi r dr times L. And then you integrate all of these shells to get an entire cylinder, so you integrate from 0 to capital R.